Like I wasn't sure that you already started or not.
Right, sorry. Yeah, I was just talking to someone else. Okay, so I'll turn on the volume a little bit just so I can hear people in case somebody wants to speak. All right, so we can get started with today's session. So, just a recap, because it's been a week. So last time we talked about natural deduction. Okay. And we talked about a few inference rules, actually a set of inference rules in natural deduction. So for each logical connective and constant, we usually have an introduction rule, we have an elimination rule, and all those, they form a set of rules. Right? So that set of rules is called natural deduction. And we've given one example how to use them to prove something. And natural deduction has some really nice properties. So two basic ones. Soundness means every inference rule is correct. And completeness means if a formula is valid, then there is a proof in natural deduction, right? So it can be used to prove every valid formula. So soundness and completeness, really powerful results. But see, completeness only says if a formula is valid, then there is a way to prove it. It doesn't tell you what is a way to prove it. Right? It only says there is a way to prove it. So if you are given the formula, how do you prove that formula with natural deduction? That's actually it's not an easy problem. So that part of the problem it's called proof search. So proof search is all about looking at a state of things you need to prove, and then decide how do you want to prove it. Right? In other words, you're given things you need to prove. You need to decide which inference rule. Right? So you've got a set of inference rules here. Which one do you need? Which one you want to choose to prove, to use as the next proof step? And then you use one of the inference rules. It will do something to the proof state. So hopefully it will make the problem easier. And then you have the next proof state, which probably is an easier problem to solve. And then you apply another rule, and then you apply another rule until the proof state has nothing, says you've proved everything. There's nothing remaining to prove, right? And this whole procedure is called proof search. And that proof search is not talked about in the theory of natural deduction. So natural deduction is called a proof theory, and proof search is another procedure. Right? Proof search is about how to use the proof theory to do things, and we haven't talked about that, and that's really important because if we want to automate this, right? So our aim goes to do automated reasoning. If we want to automate this, we need to know when to use which rule. And we're going to look at another example with natural deduction, and we're gonna see there are some potential issues with natural deduction. You know, it's really nice. It sounds complete, but it's got some issues. All right, so well, let's have a look at the two examples we did 2 weeks ago. So if you look at those examples, it's almost like we always start with well. If we look at this one, so that's one of our assumptions. That's another assumption, and we want to prove the third one. And the third one is at the bottom. And here's one of our assumptions, and here's another one of our assumptions. And that's it, right? So it's a good proof, but we're not proving a single formula here. We're proving the third formula with some assumptions. Right? So in other words, assuming something and want to prove something, that's a typical form of implication, right? So we can actually combine this whole thing into one formula, and that formula would be the first part conjunction with the second part implies the third part. All right. All right. So you assume that the first part is true. You assume and you assume that the second part is true, and then you want to prove the third part, right? So the conjunction of the first two parts implies the third part, right? And that becomes one logical formula instead of three, right? So we would say that one logical formula, because it can be proved by natural deduction, it is valid. Okay, so we're going to look at another example here. Let me have a look at the example we want to show. So the example is A implies B and B implies C implies A implies C. Okay, so we're going to write that down here. Okay, so what we want to prove is A implies B and B implies C. Okay, so these two things, so they combined implies A implies C. Okay, so this is what we want to prove. And sometimes, we don't want to draw too many brackets. So we're going to say this and, but we say it binds tighter than implication, it binds tighter than the arrow. So we can remove this pair of brackets. Okay, so we're going to say if you see an and, and you see an arrow, an and binds tighter than arrow. So this is one component, and that's another component. Right? It wouldn't be read the other way around. So the other way around would be that, right? And because and binds tighter than arrow, it's not going to be read in this way. Right? So that's just convention. Right? So it's nothing special. It's just convention. So we're going to say the left-hand side implies the right-hand side, and that's what we want to prove. Okay, so now let's think about this from the perspective of which rule we're going to use in each proof step. All right, so in the first step, what we want to prove is this formula here, and this formula is a formula of implication. All right, so we want to prove an implication, and naturally the inference rule we want to use is implication introduction. We want to introduce this implication. All right, so how do we do implication introduction? We assume the left-hand side, and we prove the right-hand side. Okay, so we're going to make an assumption. I'm going to call it A1. Assumption says A implies B and B implies C. That's our assumption. And because it's an assumption, we're going to make it in a bracket just to remind us we need to discharge the assumption at some stage. All right, we assume that this is true, and we need to do a bunch of inferences, a lot of steps. In the end, we want to prove A implies C. If we can do that, then we can use the implication introduction. Right? Introduction says you can have the whole formula like this. Implies A implies C, right? And once you apply that implication introduction, you discharge A1. So A1 is gone, right? And now we just need to fill in the blank. And so this first step is quite deterministic. We look at the problem we have at hand. We know exactly which rule we need to use, right? And the problem is now, what do we do? We need to fill in the blank. So do we do it top down, or do we do it bottom up? So it looks like we've got two choices here. All right, so we can do bottom up by doing something here with A implies C, or we can do top down by doing something here. Okay, so I'm going to let you guys choose. Give me two options. Which one would you want to go? Bottom up. Let's go bottom up. Okay. That's okay. So we go bottom up. And now what do? We want to prove that A implies C. So again, it's proving an implication. So how do we prove an implication? We're going to use implication introduction again. Right? That means assume the left-hand side and then prove the right-hand side. It's the same as what we did just now. So what we're going to do, we're going to have another assumption. I'm going to call it A2. And that assumption is just A, right? It's just left-hand side. And if from that assumption we can prove C, then we can conclude A implies C. Okay, so that's another one. And after doing that, we discharge A2. Okay, so now we need to fill in this blank. So we've got 2 blanks that we need to fill. And now, okay, do we do bottom up? Keep doing bottom up, or do we do top down?
You can keep going up because I want to see that one get resolved first.
See, the problem is now we've got this lonely formula C, and there's nothing much we can do about it anymore. All right, it doesn't have any logical connective, so there's nothing we can do about it. So we currently go bottom up. Now we have to go top down. To top down, we've got 2 things on the top. And again, there's nothing much we can do here. It's just got A. I mean, what do we do with that? All right. If it doesn't have any logical connectives, then there's nothing much we can do. So we're going to leave that alone for the moment. And we're going to look at this guy. All right. So this guy's got something and something. It's got an and, then there's something we can do. Right? It's called and elimination. Right? So you've got something, we can eliminate the and. So what do we do with and elimination? Oh, let's go back to the set of rules and have a look. What was the and elimination? And elimination is here. All right, it says if you've got A and B, then you can conclude A. And you can also conclude B. Okay, so let's go back here. Well, we're going to conclude. So we're going to say we eliminated and we can keep the left or we can keep the right. Doesn't matter, right? But let's keep the left. Keep the left. That means we're going to conclude A implies B. Okay, we're going to conclude A implies B. And now it seems like there's something we can do here. So we've got A implies B, and we've got A. Right? So we've got an implication, and we also know that the left-hand side is true. And seems like we can conclude that the right-hand side must be true. So that is our implication elimination rule here. You have an implication, you know the left-hand side is true, you conclude the right-hand side. Okay, so this is what we're going to do. Now, okay, so I'm going to move this down a little bit. Otherwise, it doesn't look pretty. Okay, so we're going to apply implication elimination. We're going to conclude that B is true. And now it seems like we get stuck here, but that's okay because once we have an assumption, we can copy that as many times as we like. All right, so we can make a copy of this assumption. Okay, copy, literally copy that. And okay, I'm running out of space. I'm going to paste it here. Maybe here. Let me just paste it here. Okay, that's the same assumption A1. So this time, obviously, we're going to keep the right part. We're going to keep the right. So we're going to get B implies C. Okay. And now this again something we can do. We know that B is true. We know that B implies C. Therefore, we can derive that C is true. So that's again implication elimination, right? That's again implication elimination. So, so I'm going to move this a little bit to align nicely here. So we've got another implication elimination. What do we conclude? We conclude that C is true. And remember, C is true, exactly what we need here. So we've already completed the proof, right? It's just we just need to connect the dots basically. So I'm going to move this whole part. I'm going to say this is exactly what we need here. All right, and then we've got this proof, and that's completed. So let's double check. So we've got two assumptions. Here we have discharge assumption A2, so that one is scam. I'm gonna draw a line on top of it to say it's discharged. And here we say discharge. Oh, sorry. So that's this one, A2. And then here we discharge A1, and we have two A1s, and both of them are discharged. And what we see in the end is that if we look up at every branch, we've got a few branches here. It's almost like it's a tree. So here's one branch. That line is very thin. Let me make it like that. So we got one branch here. We got one branch here, and we got another branch here. So it's got three branches in this tree, and all the three branches are closed. They're closed because I've discharged the assumption. So there's a line on top of every branch, and that completes the proof. Right. So now we can conclude that the formula is valid. We found the proof. Right. And you can see this whole process. Sometimes we go bottom up, sometimes we go top down, and most of the times we know which rule to use, but that's because I know this system well. So if I give it to you, you probably will have to look at the set of rules and you just think, okay, which one I'm going to use, right? So this whole procedure is not exactly deterministic. Okay, so it simulates how humans think. That's why it's called natural deduction. But it's not exactly friendly to machines. So machines don't want to have those kind of sometimes do this, sometimes do that, right? Machines like an algorithm is say, do this, and then do this, and then do this, and then under this condition you do this, and under that condition you do that. It wants everything deterministic. And natural deduction is not exactly very deterministic. Right? So we're not there for automated reasoning. So now we're pretty good with manual reasoning, good with human reasoning. But we want to step up the game. And to step up the game, so we're going to introduce another proof system. And it's got a whole different set of proof rules. And the way to use those proof rules is very deterministic. And then it's very easy to implement, right? So you can write some Python code and whatever code, and then it just runs. Right? So you wouldn't have situations like, oh, I'm here, and maybe I can do this, and maybe I can do that. See what happens, right? So the new proof system, proof theory, is called maybe I can use this. It's called sequent calculus. It's called sequent calculus. And it's invented by the same guy called Ginson. So this guy is actually quite smart. And the sequent calculus, it's got its own set of inference rules. But again, before we talk about the inference rules, we're going to fix the format. So what is the format of inference rule in sequent calculus? And it ends up, it's quite similar as in natural deduction. So we would again write an inference rule in this way. So there's some premises, P1, some other premises, P2. You can have as many premises as you want. So one premise is basically something you have already proved, or something that you assume is true, right? And then from those, you get the conclusion, right? So we always write a premise on the top of the line and the conclusion below the line. And we write the name of that inference rule on the right-hand side of the line. So that's the general format of an inference rule, okay? Now, every premise and conclusion in sequent calculus is called a sequent, okay? It's called a sequent. And this English word didn't exist before this. So historically, I think Gentzen named this the calculus of sequences in German, but it's in German, right? So it translates to the calculus of sequences. So being a sequence, it's a list of things, right? It's actually a list of logical formula. So a sequent is basically a sequence or a list of logical formula. And then there's another guy called Kleene, and he's American, so he knows English well. So that guy's called Kleene. Okay, Kleene. And he coined this word called sequent. He says a sequent is a sequence of logical formulae. And this guy is actually, he was one of the top, mathematicians as well. And I'm sure if you don't know him, you probably use something named after him. So if you use, let's say, regular expressions, in regular expressions, one of the fundamental ways to construct expressions is called a star. Okay, so if you write a star in the regular expression, it means 0 or more copies of A. It repeats 0 or more times. And that star is called the Kleene star. It's invented by him. Okay, he's a very good mathematician.
Regular expression is like what we use for search.
For search, for
yeah.
pattern matching.
Yeah.
Right. So if you do, let's say, a website, you want to pattern match this guy's email address. You say the email address must be of some sort of pattern.
Yeah.
Something at something.com or something.
Yeah.
Right. So you would use a regular expression to express, the format of things you want to pattern match.
Yeah.
And same as the password. So you would say a password must be, at least 12 symbols long, must have uppercase letters, lowercase letters, some symbols, numbers.
Yeah.
Right. So you would all use some regular expressions to pattern match things. So it's very useful. It's invented by Kleene. Okay. So sequence. Now, except sequence got a little bit more than just sequences of formulae. So it's actually written in this format. Okay, so I'm going to write it this way. What is a sequence? So a sequence is defined as not one, but two sequences of logical formulae. So I would probably write A1, comma, A2, comma, A3, comma, ... AN. So that's one sequence. And then there's this symbol there. And then we have another sequence, B1, comma, B2, comma, ... comma, BM. Because you may have a different number of items on the right-hand side, because N and M. And that symbol there is called a turnstile. It's like the turnstile you use when you go to Subway. So we probably don't use that anymore, but it's called a turnstile. And to simplify, I think, to simplify everything, I'm going to redefine a sequence. Right? So originally, it was two sequences. I'm going to say it's two sets. Okay, two sets instead of two sequences. So there's a slight difference. Okay, so there's a slight difference. So a sequence, or sometimes we call it a list, or in programming languages, it's an array. Or it's a list of things, and the order matters, right? And the duplication also matters. So that means if you've got A1, A2, A2, A3, it's different from A2, A1, A2, A3, because the order is different, so it's different. The order matters, and duplication also matters. So how many copies you have for each single thing is also important. So these two sequences are also different, okay? And we have another concept called set. It's multi-set. So in the multi-set, the order doesn't matter. So if you write A1, A2, A2, A3, it's the same as A2, A1, A2, A3. Okay, so the order doesn't matter, but duplication still matters. So this is still different than A2, A1, A3, because one you have one copy of A2, the other one you have two copies of A2. So duplication still matters. Okay. Now comes our next concept of a set. So in the set, order doesn't matter, and how many copies you have for a single atom that also doesn't matter. So the above is equivalent to let's say A2, A3, A1, the same, right? So the order doesn't matter, duplication doesn't matter. All right, so I'm going to simplify everything by saying these two are sets instead of sequences. So I'm going to simplify that. The order doesn't matter, and how many copies you have for a single formula also doesn't matter. Okay. And now we've got the concept of a sequence. So we can actually map it to a logical formula. Okay. So the way you interpret a sequence is every comma on the left-hand side is a conjunction, and every comma on the right-hand side is a disjunction. And this turns out is an implication. Okay, so a sequence in the above form is interpreted as a logical formula A1 and A2 and ... and AN implies B1 or B2 or ... BM. Okay, this is how you understand a sequence. Right, so this is everything you need to know about a sequence. Okay, so that's a sequence. Now we need to have the inference rules with sequence. Right, do we have any questions here? Okay, that's all right. So, okay, yeah,
That's all right.
that's okay, that's okay.
And I will be back.
Okay, so we need to have a bunch of inference rules with sequence. Right, and the first one we're going to have is to look at the logical constants. Hello. How are you? Good, thanks. So we're going to look at the logical constants. So we have truth and we have falsity. Okay. And with sequence calculus, for every concept, we're going to have an inference rule when that concept appears on the left-hand side, and another one when the concept appears on the right-hand side. So basically for truth, we would have a truth on the left, and then we would have a truth on the right. Okay, so let's have a look at what happens when we have truth on the left-hand side. So I'm going to write a gamma to represent a set of logical formula. If you have truth on the left-hand side, then delta is another set of logical formula. Okay. And if you have that, and it's the same as having just gamma and delta. Because something and true is the same as saying just that something, right? So and true doesn't tell you much. And in fact, we actually don't need to use this inference rule at all. Because, everything is in sets. So how many things we have on the left-hand side of the sequence actually doesn't matter. So, technically, we can say we don't need this rule at all. Okay, we don't need this rule. So I'm going to draw a blue cross to say we don't need this. It's not because it's wrong, it's just we don't need this. Okay, so what about when we have truth, but on the right-hand side? That says from something you can imply that this truth or this delta. Okay, and the rule says then you can, if you have that in the conclusion, then you can finish your proof. Okay, if you have it in the conclusion, then you can finish the proof. So the other one is falsity. All right, so the rules for falsity is exactly the opposite. We can have gamma and false turns down delta. If you have falsity on the left-hand side, then you can conclude your proof. Okay, and we don't need any falsity on the right-hand side. Okay, we don't need any falsity on the right-hand side. Okay. So we've talked about the two most basic inference rules. So one is for truth, one is for falsity. And the one for truth may not be exactly intuitive. Okay, so maybe it's worth it to talk a little bit more about how we derive these kind of rules. So sequence says the conjunction of the left-hand side implies the disjunction on the right-hand side. Okay, and when we do reasoning with sequence calculus, we're not going to say sometimes we do bottom up, sometimes we do top down. We're going to fix one direction. So we're going to go bottom up all the way. It's always bottom up. And the way you read the proof is as if we're doing something called refutation. So we're trying to prove that a formula is wrong. Okay, so you give me a formula to prove, and I'm going to assume that it's wrong and see if where I end up with. So I'm going to say, I think it's wrong. And then I'm going to try to prove that it's wrong. And if I cannot, then it's valid. So that's the idea.
That's kind of the opposite to what we were doing before. Yeah, that one. Where
Sort of.
Assuming true and then.
Sort of, yeah. So refutation. We assume that the formula is wrong, it's not valid, and then we see where we end up with. We see that if we can get a counterexample, if we cannot, then it must be valid. Okay. So when we start the proof, if we want to prove a formula A, we would prove nothing turns out A. Okay. And then we would go bottom up and build a tree. So what is this nothing turns out A? It says nothing implies A. Okay. And if we go with refutation, we're saying we want to make A false. Okay, and then we see if there's a way to make A false. So basically, the other way you can understand the sequence when we read it in the refutation way is that everything on the left-hand side is true and everything on the right-hand side is false. Okay. So that means, if we add not here, not something or something or something, we apply De Morgan's law, it would be not B and not B2 and and not B and. Okay, so that's why we say everything on the right hand side is false, and then here we don't do anything, so that's everything on the left hand side is true. That's how we read a sequence when we do refutation. Okay, and that's also why if you have truth on the right hand side, then you've got a problem because you're assuming that everything on the right hand side is false. Truth can't be false. So you've got a problem, so you close that branch. All right, so we're saying we close it. So we're going bottom up. Whenever we see a truth on the right hand side, something's wrong. We have to close that branch. That branch cannot happen. And if you see a false on the left hand side, so we're assuming that everything on the left hand side is true. And false cannot be true. So if you have false on the left hand side, then something's wrong. Okay. So we actually don't need this whole thing. So let me just simplify everything. I'm going to move this up there. Okay. So that's the rules for truth and false. Truth and falsity. Now, what about, say, what else do we have? Negation. Let's have negation. So for everything, we're going to have the symbol on the left, the symbol on the right. So what happens when we have a negation on the left? Okay, so delta and gamma are sets of logical formulae. So they're not one logical formula, they're sets of logical formulae. All right, so now we have not A on the left-hand side. What do we do with not A on the left-hand side? That's simple. We just move it to the right. Okay. As a sequence is everything on the left is true, everything on the right is false. So not A is true means A is false. So we just move it to the right. Okay, that's what happens when we have a negation on the left. And if we have a negation on the right, then it's symmetric. Okay, so not A is false. That means A is true. So we move A to the left. Okay, so we always read it bottom up. That's where we're going to read things. So negation is extremely simple, right? Next we have conjunction. So we have A and B. Now, comma on the left is and. So having A and B here is the same as having A comma B. This comma on the left is conjunction. So that's how we do it. That's how we do conjunction on the left. And if we have A and B on the right, then that's a bit complicated because comma on the right is or, it's not and. Okay, so if you want to show that A and B this thing is false, because it's on the right-hand side, then you need to show that A is false, and there's another case of B is false in the refutation. So it splits two branches. Okay, so that's what happens when you have conjunction on the right. Okay, so this also works if you read it top down. Actually, if you read it top down, it says from something I can prove A, because tensile means implication. I can prove A, and I can also prove B, and then I can have A and B. So it goes both ways. Now disjunction. So what if you have A or B on the left? Now comma is conjunction on the left, so you can't just convert or to and. So if you have that A or B is true into the refutation, then you need to say there are two cases. What if A is true? All right, and another case is what if B is true? So that's what happens when you have or on the left. It's actually symmetric to and on the right. So everything is very symmetric. So that's what I like about this. Everything is symmetric. And if you have or on the right-hand side, because comma is an or, so you simply say that is A, comma, B, comma, delta. And that's symmetric to and on the left. Okay. I think we need one more thing. That's for implication. So what is implication? We have A implies B on the left. What happens then? So I think the easiest way to look at this is remember A implies B is equivalent to not A or B. All right, and that's just or. So that's just or, and that means what you have here is actually gamma not A turns to delta, and gamma B turns to delta. All right, and then we have this not. So what do we do with not? We just move A to the other side. So we have gamma A comma delta and gamma comma B turns to delta. So that's exactly the rule for implication on the left. Now implication on the right, we have A implies B on the right. This one is quite straightforward. And again, you can look at this as A, not A or B. So you can have this following the or, and then you can move A to the left. So this is what it looks like. Okay, so that's implication on the right. And those are everything you need to know about sequence calculus. So with those set of rules, again, it's sound. So every rule is correct. Second, it's complete. So it can prove every valid formula. So let's do the same proof. Well, not same proof, but let's prove the same formula that we proved at the beginning of today's session. So I think that formula is A implies B, and B implies C implies A implies C. All right. And if you look at the formula here, it actually just says implication is transitive. So transitive means you go from A to B, and then you go from B to C, then you can skip B. You can go from A to C. All right, so that's transitivity. Okay, so this is the formula we want to prove. And in refutation, we're going to put it on the right-hand side. This is where we begin. We begin by proving nothing turnstile this formula. Okay, so what do we do? Now remember, this is an implication. Okay, so we have implication on the right-hand side. Okay, on the right-hand side, and naturally we're going to use implication on the right. That's extremely straightforward, systematic. You have some logical connective, and depending on which side of the turnstile it's at, you apply that rule. So you apply implication on the right, what do you get? So you basically move A to the other side. You move the left-hand side to the other side of the turnstile. All right, so here you move the left-hand side to the left, and you do the same down here. So you end up with A implies B, and B implies C, turnstile A implies C. And now we have something on the left, we have something on the right. So technically we can apply and on the left or implication on the right, and it doesn't matter which one you apply actually. You'll get the same proof eventually. So let's just say we apply and on the left. And on the left says that we just convert that conjunction into a comma. Okay. And then there are two logical formulae you can play with on the left. There's one you can do on the right. And which one you use, still, it doesn't really matter. You can do implication on the left. You can also do implication on the right. Although some of them will end up having a shorter proof than the other, but both will end up having a proof. So you don't have to worry about applying some rule and then you have a dead end, you have to backtrack. That doesn't happen, right? So the only difference is sometimes you have a shorter proof, sometimes you have a longer proof. So I'm going to say we do implication on the right, and then we have we basically move this A to the left. And then now we can only do implication on the right, on the left. There's nothing on the right. So we do implication on the left. Sorry, that's actually this rule here. I should call it implication on the left. All right, and you can do it on A implies B, or you can do it on B implies C, and it doesn't matter which one you do. It doesn't matter. So let's just do it on A implies B. Okay. What's going to happen is this A is going to be moved to the right-hand side. And then on the other branch, you're going to have B on the left-hand side. And the remaining part would be the same. Okay. So I'm going to copy the remaining part. The remaining part is this. So I'm going to copy the blue part there. And here we have C. And here we have B implies C and A, and then C. Okay. Oh, I forgot one extremely important rule, and I missed. It's called identity. All right, it's called identity. So if you've got some logical formula on the left, you got the same logical formula on the right, then you can conclude that that branch cannot happen. Because you can't have something that is true and something that is false at the same time. All right, so that cannot happen. And look here, you got A on the left, you got A on the right, so that cannot happen. That's ID. And then we only have one branch that is open. So again, we're gonna apply implication on the left. So this time, see, the left-hand side goes, so the left-hand side of the implication goes to the right. So we're gonna have something, so this B would go to the right-hand side of the turnstile, and that C would move to the left-hand side of the turnstile. And then I copy this blue remaining part. So on the left, we have AB, A comma B. On the right, we have C. And here it's the same. On the left, we have A comma B. On the right, we have C. And then here we have B on the left and on the right. That cannot happen. Here we have C on the left and on the right, and that cannot happen. All right, so in this refutation proof, eventually we show that there are three possible ways we can refute this formula, and none of them can happen. So therefore, the formula must be valid. Okay. And so in the refutation proof, it only goes bottom up. And if you see a formula with a logical connective on the left, you apply the left rule. If it's on the right, you apply the right rule. And it doesn't matter which order you apply them. Eventually, you always have a proof. Sometimes you get a shorter proof. Sometimes you get so the order you apply rules doesn't affect what's called provability. You can always prove it. It's just sometimes it takes you longer to prove it. Sometimes it takes you shorter to prove it. But you can always prove it. So you can literally just write that into an algorithm, and they can do automatic reasoning for propositional logic, and it will just work. Right? So systematic, you don't need to make decisions. Computers don't have to make decisions. Right? It just goes in the way you want it to go. So that brings up, very close to we're pretty much already in the automatic reasoning era now.
Oh.
Yeah, so that is for propositional logic.
And so you can prove or disprove the same problems with both the versions that we've looked at.
With both natural deduction and sequent calculus, yes. If you've got a formula, you can do it with natural deduction. You can do it with sequent calculus.
Will always come to the same conclusion.
Well, yeah. So if a formula is valid, you will always be able to prove it in both systems. It's just with sequent calculus, it's a bit more friendly to machines.
Yeah. Right.
It's a bit more friendly to machines. It's a very systematic approach to do it. So I think that's pretty much all I want to cover in this session. And I think that's most of it I want to cover for propositional logic. To come next week, we'll probably look at some other logics and then some other ways to prove things. And sometimes I think I want to run a session that is not very, mathematics heavy. So we can look at some what's so-called non-classical logics from a more philosophical point of view.
Yeah, cool. That would be good.
Okay. Yep.